Hello and welcome, people. My name is Zach. There's my email with my actual first name. Zach is my nickname. Don't bother. I'm your new lecturer for Foundations of Audio Processing, which is my favorite topic ever. Which means I have tons prepared for today. Meaning I have no time to introduce myself. Once we get to have a beverage, I shall hopefully say interesting things about the self, but instead let me say plentiful interesting things about amplitude processing. So first of all, I'm going to introduce an engineering term, linear time invariant systems, not to scare you, but instead to get you comfortable with some of these terms. If you get into reading about DSP, you might find these terms. If you just use DSP, which is digital signal processing, to make interesting sounds and have some fun, you might not see these terms. Nevertheless, we're trying to build a good foundation here. So I'm briefly going to discuss these two terms. So linear processing has everything to do with transformations of signals such that things remain intact, mostly. Okay, so linear and nonlinear, I'm gonna say more things about this. First thing to figure is that the linearity means typically that proportions hold before the process and after the process. So in essence, what you have is that the signal is processed and it will be processed in the same way regardless of the input amplitude. Okay. Time invariant, the other term that constitutes the LTI systems, has everything to do with the idea that the system does not change behavior in time. So whenever you start a process, it will always do the same thing. There is no time variance. Okay. So about linear operations, nonlinear operations, can we think of something which is nonlinear? In other words, something that processes the audio in a way that will change depending on the input amplitude? The answer is, I can think of a few. Not sure about you, but in essence, you can probably think about just the basic amplifier. If you overdrive it, if you push the signal too hard, it will distort, it will suddenly sound different. Okay, so what we're looking at is systems where, depending on gain, the timbre, the color of the sound, does not change at all. Now, if we broaden the perspective here, many systems are nonlinear. In fact, every physical system is nonlinear to some extent. Typically, if my voice itself, if I talk at a regular level, it has a certain timbre, but if I start screaming, it will have a different timbre. Now, if I turn down the volume on the screaming, I will still appreciate that it was screaming to start with. So it is evident that the timbre has changed, not just the actual gain of the signal. Okay. Now, as far as the time-dependent processes go, what can we think of? Well, in fact, all the processes, all the physical systems will slightly vary over time. My voice as a physical system definitely will. If I suck some helium, even more so. Typically, I don't know, valve amplifiers need some time to warm up. So during the warm-up, the quality of sound will change. Also, any other amplifier, if you leave it on for 50 years, it might change as well. So however small the difference is, there always are differences. Now, evidently, in digital signal processing, we will be looking at bits that are reliable in terms of time invariance and systems that are deliberately made to change behavior over time. Okay, so basically the linear operations that we can look at in terms of arithmetic, basic mathematics, are multiplication, which changes the gain of a signal, and addition, which changes the DC offset. These two are the most crucial building blocks of all signal processing in this context. Now, there are other linear signal operations. Delay is linear. It does not change the timbre of the sound based on the incoming amplitude. Although you can produce a more complex process with delay if you introduce feedback and dry signals into the mix, which makes it slightly different. Nevertheless, still linear, but then again, time variant. Filtering, you might find this surprising, but is actually a linear operation. So filtering constitutes attenuation or indeed increase of gain for certain spectral regions. But all sorts of attenuation, be it overall gain change or just in a certain frequency range, is linear. Time reversal is another example. Again, even though perceptually the sounds may become rather different, technically it is a linear operation. So let's talk about multiplication and addition, hopefully our two new best friends. Here is a graph of a little sine wave that extends from -1 to +1. This is typically the range of values for digital audio. And in digital audio terms, you will often hear the words scaling and offsetting. Scaling is multiplication, offsetting is addition. Okay, so if we scale the signal, we change its extent. And because audio signals are what we call bipolar, going between +1 and -1, what you get is that multiplying with a number larger than 1 extends the signal in both directions, negative and positive. Multiplying it by a value lesser than 1 will actually make it smaller, thus softer, both sides. But if you just multiply, you're not going to change the offset, so the signal will be neatly centered around 0. Okay, so multiplication is fairly safe for audio signals, while addition is not necessarily safe, because what you do is you shift the signal up and down, you offset it, and you might understand that these waveforms actually describe the motion of the loudspeaker cones, which means that you will have potentially some damage to the cone because you're pushing it out more than you're pulling it back in. So the 0 point is offset. We call this the DC offset, the direct current offset. So you have to be very careful and do not attempt to offset audio signals. Evidently, offsetting of signals will be useful, and we will do this to control signals, and these distinctions should become clear fairly soon. Good, so addition. The basic thing we do with addition is mixing. So what I have here, top left, is you see a little sketch. You will see an increasing number and increasingly more complex flow diagrams, or there's many names you can call these. And what you see there is arrows which signify the way the signal travels to and from components. And typically components will be boxes or these circles. In this case, what you see is the first most important component, the addition, the plus. And evidently in PD you will see these diagrams as well with a different orientation. And it's not necessarily about complicating stuff, but it's actually about these types of diagrams being transferable. And if you talk to audio engineers who don't necessarily use PD or otherwise audio programmers, they will all understand a basic diagram, whereas a PD patch is a more specialist thing to understand. Okay, so what we see there is two inputs, two signals coming in, both into the plus, and out goes the output. So actually, if you sum signals, you are mixing them, which means that they will come through unaltered, typically. Okay, so there is a sketch below about how this looks in terms of the waveform. So typically, when we talk about adding two signals, or indeed multiplying two signals, what we're getting at is taking each sample one by one and doing the given operation to each sample of the other signal. So kind of pairwise in sync, this is what happens. Evidently, an audio signal is about 44,000 samples per second. So quite a lot of math going on there. Now, multiplication will be the basic tool of changing the gain of a signal. Okay, so here's a little sketch where you see the multiplier, you see the incoming signal, you see the outgoing signal, and you see a little dial, which is typically user-controlled tool, and you see how the value which is dialed in alters what's happening. So if you multiply a signal with a 0, so all the samples times 0 will give all zeros, that's essentially muting. And then you see multiplying by 1 is leaving the signal fully intact. 0.5 will give us some attenuation. And evidently, values larger than 1, which are not presented here, will give you an increase in gain. So in order to get used to understanding, figuring out, even coming up with these basic graphs, let's take it step by step. So here's a sketch of two-channel attenuation. So typically when we do stereo processing, what we will do is we will have a single set of controls, mostly, but we will actually have a doubled set of processing components. So in this case, the only processing component is a multiplier, allows us to change the gain, but you see how we are keeping the two channels separate in a totally isolated processing chain, but they are both controlled by the same value, which means that I actually have a stereo gain knob just there. Now, if you want to mix and change the gain control, this is the sketch you're looking at. So both inputs have their own gain control. You could add one in the end. It's a basic puzzle, I guess, fairly straightforward, nevertheless worth looking at just to start to internalize these representations. So getting progressively more complex, here is stereo mixing. Okay, so what we're looking at here is that there are two inputs, but each input has two channels, two signals. So actually you see 4 signals coming in. Should do it with this hand, right? 4 signals coming in. And actually every signal has its own gain stage. Okay? The reason is that you cannot process both left and right signal through a single gain stage. In other words, by using a single multiplier, because that would mean that you have mixed the channels together. If you send both channels into a single multiplier, and once you do that, there is no way of separating them out together. Okay, so that's what you see. So the input 1 has 2 channels, 1 gain control that controls both channels. Second input, same at the bottom. And then you see how when they are summed, the left sums with left to get output 1, and the right sums with right to get, this is really funny, output right. Okay, so observe this sketch and see how evidently it is sufficiently simple for you to get there, but it might be tricky to think everything through, and you might be hasted initially thinking that, oh, well, it's just mixing 2 things. But internally, there's a few more things that constitute this process. Okay, so getting further on with basic amplitude related processing, here is panning. So briefly, what is panning? Why do we do this? You probably know these things already. Nevertheless, it is crucial that spatial distinction helps separate sources for listeners, often giving us a sense of greater detail of the audio. There are a few interesting things that you might not be aware of. Actually, you can go beyond the loudspeaker, beyond the left and the right speaker with certain phase inversion techniques. Necessarily, you will have to have a really neat listening spot. You can actually produce height and depth. We're not going to talk about this, but worth knowing that with certain filtering techniques, you can actually have a sense of elevating a sound source even though the speakers are in a single horizontal plane. You can get a great sense of envelopment. Similarly, plenitude of techniques there. And if you are lucky and have good speakers and do things well, you can actually get a sense of presence of sound sources, acoustical sound sources, without necessarily realizing that it's a reproduction. So you can get quite a believable sound stage and quite a believable presence. Okay, so we're briefly going to talk about amplitude-based panning. There are many other ways you can do this. I won't go into this, but there is a link. I have a plugin, if anyone's still using 32-bit plugins, an audio unit plugin, Autopan, which has 5 different panning procedures embedded, and you can actually play the cues in against each other and have some fun with that, hopefully. Okay, so let's look at the sketches of amplitude panning control. So what we're looking at is 2 gain stages. One signal is being split into 2 gain stages. Evidently one is left, the other one is right. And there is a little table which spells it out for you in terms of when do you perceive sound coming from which direction. Evidently, to get the sound centered, again, you need a good listening environment and probably a good pair of ears, which I do not have anymore. For me, things are already a bit on the side, playing drums too much and loud sound sources otherwise. Okay, so, and here is the sketch which shows you the signal processing that can achieve that for us. Okay, so what we have then is signal coming in, being split into 2 gain stages, and out of the gain stages you get your 2 channels left and right. So this bottom part is what you can call the audio chain, and the top part you can call it the control chain, because it's actually no audio signals running there. It's signals that come from the dial, from the user control. Okay, and what you see there is that there is a box with a little equation which inverts this range of 0 to 1. So when the dial is at 0, then the right channel gain stage feeds straight from it, meaning it has a 0, meaning it mutes the right channel. And if the dial is full right, then the dial outputs a 1. So the right channel gain has value 1, which means full on signal. Whereas through the equation we get y, which is output, equals 1 minus x, which is the input, which means that 1 minus 1 is 0. So out of the equations we get a 0, meaning that the left channel will be muted. And then evidently halfway, 0.5. If that is the case, then both gain stages have a 0.5, which means that they will have an equal loudness on both sides, which means that the sound source is centered. Okay, so I guess this should be fairly straightforward. So you see how you actually have one signal source, one control source. They both fork out, so to speak, and then the whole process yields 2 audio channels straight out. Okay, now when we get to discuss more complex sketches like this, typically what we can do is encapsulate to make things transparent. So what you see there is a little box which is called pan. So what we've just looked at is one of those pans. Okay, and then because we are mixing multiple stereo channels, we are just showing the encapsulation there, and then we can show how things are being added, how channels are being mixed. A few more basic amplitude-based sketches. Okay, so here is the control of dry-wet signals. So input signal is split into 2. One goes through an effect, the other one doesn't. And each of these has their own gain stage. Evidently, multiplication I dub gain stage. And then, somewhat similar to the previous sketch, we have this inversion of the 0 to 1 range to control the amplitude of these 2 paths separately in an inverse fashion. So when one is full on, the other one is muted, vice versa, and there is a way to blend between the two. And in this sketch, there is an extra output gain as well. Okay, so as far as this blending goes, there is a bit more detail. You can get into other slightly more accurate ways of doing the panning or the dry wet control. With this one, what you may notice is that there is a dip in the middle, which is the property of these linear panners. And there are other solutions, but we'll try to keep this fairly practical and straightforward and won't go into too much detail. If anyone's interested, you can probably look up cosine law panning fairly easily, which is typically the industry standard here. Okay, so we've looked at some linear operations, typically gain-based operations. So let us think about the nonlinear operations, and we will get to this idea of linearity in a second. So typically everything that has to do with distortion is nonlinear. The main characteristic of nonlinear processes is that there will be new spectral components. Okay, so filtering, where you attenuate different frequency ranges or boost them, is still linear because there is no new signal content. With a nonlinear process, there will be new signal content. That's the crucial thing here. Typically, harmonics are generated. But if you look at the list here, there are things like subharmonic distortions as well, aliasing distortion, which you might have heard of when you studied A to D conversion. And there's many ways to distort a signal using a nonlinear transfer like that. And in each case, if you put a single sine wave through a distortion, a nonlinear process, you will get more than a single sine wave. Whereas if you put a single sine wave through any linear process, including filtering, you will get only a single sine wave out. Okay. Now, the other class of nonlinear operations, which are not explicitly distortion, but do induce distortion, are dynamics processes. We will talk about these in some more detail. The main difference here is that both processing techniques have a nonlinearity, and the distortion type processes, they operate on each audio sample one by one, whereas the dynamics processing operates on averaged out amplitude values. So typically you can use any distortion algorithm in the context of dynamics processing and vice versa, which will be quite apparent once we look at the transfer functions. Okay, so the transfer function is the key here because it shows you the relationship between input and output. Input horizontally, output vertically, X and Y fully matches what you might have studied with mathematics. So it's a plot And here it's quite evident that a linear process will have a straight line as its plot. Okay, so if you look at the leftmost linear transfer, you will see that each input value, so if you take a value halfway the input axis as displayed, and you map it onto the straight line, onto the graph itself, and then map onto the horizontal line, you will also be halfway up. So if there were numbers, which there are none currently, just to make things simple, each value on the input axis would map to the exact same value on the output axis based on tracing via the graph. Okay, so that's your linear transfer y equals x function, if you like the math bits here. So as a brain exercise, these are not very useful transfers, but you can consider a horizontal line to be a transfer function. And if you think it through, what that means is that regardless of the input value, the output value is always the same. And if you place a vertical line in your transfer function, you can consider it being a type of triggering transfer, meaning that the output is always 0 except when the input value hits, well, this could be 0.5 here, it's halfway somewhere. Okay, so it's a kind of a triggering type function. As a matter of exercising the understanding of input and output axes. But here are some more useful transfer functions. So what we have here is a steeper line, which means that if you look at it, if you're halfway on the input axis, the graph will map to the full-on output. Okay, so it's amplification by a factor of 2. Evidently, if you had a less steep line, less than 45 degrees, that would be attenuation. So you can read how these graphs specify the process. In fact, transfer functions are very often used in engineering to consider a black box. If you have something you don't know what it's doing, one of the first things you can do in order to start to understand what's happening to the incoming signal is to plot the transfer function, which means that you take all the possible input values, input voltages or floating point numbers if it's a digital VST or something similar, and for each input value you actually plot the output value on the vertical axis, and you get some kind of a graph that you can read and start to interpret the function of the system. So another straight line facing downward, sloping downward, is an inversion. So what you see here is that as the input value grows, the output value becomes smaller. And then the third one, the staircase transfer, is actually quantization. So you can try to read this one as well. So you see, if you have two input values which are really close together, it might be that for those two close together values, you get the exact same output value. So you get this kind of quantization going on. And what you see then is that quantization is not linear. Okay, a staircase is not a straight line, no matter the fact that it kind of takes that shape. Overall, it is crucially nonlinear, and that's where aliasing distortion links into, because you will necessarily have some extraneous, newly formed spectral components if you perform quantization. And then the final three transfer functions here will be the ones that you might have seen previously, which relate to dynamics processing. So there is a compressor, there is a gate, and there is an expander. But I will talk about these in more detail in a bit. Okay, so we've discussed briefly the linear, the nonlinear transformations. Let's look at the distinction between time varying and time invariant transformations. essentially these two properties, linearity and time invariance, are not necessarily linked. They can be quite independent. Nevertheless, in engineering, in signal processing, they are held together to highlight the simplest transformations, which have some basic properties which can be exploited. So in this context, the time-varying transformations typically end up being containing some type of modulation. So here we have three basic ones. We have a tremolo, which is amplitude modulation, changing the gain as the signal plays, vibrato, pitch modulation, changing the pitch, and auto filter, where you change the cutoff frequency of a filter that is processing the sound. Can you think of a real-world example of a time-varying transformation? I kind of said a few things about, amplifiers breaking down or warming up. There's probably a few more. Let me know if you thought of a few. So let's look at how this modulation can be made simple to understand. Essentially, what you're doing is replacing a dial, something that the user may have controlled, with a signal which automates the control. So typically, we are looking at periodic signals, like sine waves and other waveforms, which will then allow you to control the frequency of the modulation, how rapid, how fast it is. And also, typically, what we have is a way to control the depth of modulation. In other words, the amount of modulation that is being done. So tremolo is the first basic one here. It is amplitude modulation at slow rates. If you make the tremolo too fast, you typically don't call it tremolo, you call it amplitude modulation, because suddenly we cannot track all the peaks and troughs of the modulation. We cannot hear that the signal is becoming louder and softer because this is happening too fast. And in this case, the timbre starts changing. We'll talk about this at some later stage. Okay, so what are we looking at then is just a basic sketch of a gain stage, changing the gain of the signal, but instead of a dial, we supply a signal that will control the change of this gain, and this is what we call a modulator signal. So typically we use symmetrical periodic waveforms like sine wave and triangle. So what do you think might be the issue with the square and a sawtooth based modulation in the context of changing gain? Well, what you have with those two functions is that they have a really sudden drop. And if you change the gain of a digital signal really quickly from one sample to the next sample using a huge jump in gain values, you will get a discontinuity, a click will occur. This won't happen if you do it with the analog dial. If you do it too much, you're probably going to wear it out and it's going to start making noise. But typically you cannot get to this click. But this click, the discontinuity of an audio signal, is something that you can appreciate in the analog domain if you have the guitar amp on and you plug in the cable. Right, so you get a sudden jump and you get a broadband signal, meaning it has bass, mid, highs, it has everything. It's a very short signal. We'll probably talk about impulses like that at a later stage. So here's a sketch of a tremolo whereby you see on the bottom you see the actual signal, audio signal chain. And again, the audio signal chain here is nothing but a single gain stage. Input, multiplier, output. What you see on top of that, again, is your control signal chain, where we have a function generator with a waveform W, and you see it has an input letter F, which stands for frequency. Typically we could have a dial in there, we can have a value like this, it doesn't really matter. In any case, it has a variable frequency, which will be our modulation frequency control. And then what you see is that this control signal is being multiplied by a value, which is the depth value, and it is being added another value, which is the offset value. Okay, and up in the graph, what you can see then is how this signal, which is initially ranged between -1 and +1, like most oscillators, suddenly changes values based on the incoming signal. So you see, because if I multiply my audio signal with the bipolar modulator going between -1 and +1, then I will get some phase inversion when I multiply with a negative number, right? So it's gonna go beyond a basic tremolo, really. It's becoming a ring modulator. So what we actually want to do is have a unipolar modulator, meaning that it has only positive values. It doesn't go into the negative values. And by having the size of this modulator, the range, controllable, we are actually controlling the depth, the amount of modulation, the distance between the loudest and the softest. So if you want full depth, then you would have a modulator between 0 and a 1. But you might want to have lesser depth. So that's why these controls are needed here. So here is an example with numbers with the Sawtooth modulator. So what you have there then is a Sawtooth running at 10 Hertz. So you see all the numbers are there. Then it's multiplied by 0.2. And then you see the top graph displaying that. So from -1 +1 range, we get a range -0.2 to +0.2. And then we add 0.6. And then we get a range between 0.4 and 0.8. So that's the top right graph, where you see that the Sawtooth wave has shifted up. And if we use this signal to multiply the incoming audio signal, then you see that the incoming audio signal has slightly reduced in its maximum amplitude, and it actually shows this pattern of gain reduction that is induced by the Sawtooth wave. So here is a sketch of how this waveform looks like when we are increasing the modulation rate. So you see that the duration of each Sawtooth drop is becoming shorter, meaning that the frequency is becoming higher. And then at the bottom you see the increase of modulation depth. So you see that the distance between, or I should say the duration of the Sawtooth drop is the same, but the depth is changing. The distance between the highest and the lowest amplitude is becoming increasingly larger. Okay, so let's have a brief look at an Autopan effect right here. So it's fairly similar in that we have a modulation source, we have an audio signal. It is also similar in the way that there is nothing but gain stages in the audio processing chain. So we're duplicating a mono signal. Each new signal has its own gain stage. And then what you see here with the Autopan is that we use an inversion. So first we modify the control signal to be in the range 0 to 1. So if we multiply by 0.5, add 0.5, we get a range 0 to 1 from range -1 to +1. And now that we are in the range 0 to 1, we can do an inversion by doing 1 minus the input value. And if we do that for one side and we don't do an inversion for the other side, we actually get these values going up and down out of phase. So you see that the resulting waveform for the left and the right channel will make it such that this sound source suddenly pans from left to right automatically at a given frequency potentially, and with potentially some controls over the width of the Autopan, which makes it a bit more complex. We won't quite go there right now. Okay, so those were the linear processes. Now let's look at further amplitude processing techniques, which are nonlinear and focus on dynamics processing. We'll have more to say about distortion type nonlinearities later on. Okay, so as I mentioned, the basic thing we're doing here is changing the gain of the signal based on its averaged amplitude. So typically these processes are used to change the dynamic range. Initially they were invented in order to be able to work well with tape. Tape has a fairly narrow dynamic range. Dynamic range meaning the difference between the loudest possible sound and the softest possible sound. So on a tape, if you push it too loud, what you will get is saturation. The tape won't be able to magnetize further, which is a kind of a soft clipping actually. And at the bottom of the dynamic range you have the noise floor. So tape has this inherent hiss. So at some point the signal will get buried into the hiss, details lost, maybe even rendered inaudible. So there's a limited dynamic range. And what they came up with, the engineers came up with a solution of doing a compression before recording onto tape and expansion once the tape is being played back. And with minimal anomalies, this actually has worked. So you could actually reduce the problems of tape hiss by using these techniques. So that's a little bit of history there. But most recently, probably everyone knows, compressors are used to induce a sense of presence, loudness, force. There are some psychoacoustical parallels here. So our ear also compresses quite a bit. There are similar mechanisms in the physiology of the ear. So when a very loud sound comes in, stampedious reflex kicks in, and the little ossicles, the little bones in the ear, the muscles get stiffer, and they don't allow them to move as much. So in a way, the compression artifact is something that we recognize as meaning that the incoming sound was extremely loud. There's quite a few ways you can come to describe everything that happens with dynamics processing. So inherently it is nonlinear, and therefore it will also induce distortion. It will induce new spectral components, maybe unnoticeable, but by default it will. Okay, so let's look at a basic transfer function of a dynamics processing effect in a bit more detail. So hopefully the input and the output axis reading is fine by now. So what we have here then is labeling of these axes. So you see we have input envelope level, typically in dB. So this is your averaged amplitude value. And then we have the output averaged level. Okay, so this is the transfer function which describes what it does to a signal. Now what you see then on the input axis horizontally, there is a point labeled threshold. And below that threshold, that is to the left of that line, what you have is a linear transfer. So the signal remains fully intact until it reaches the threshold. And once it reaches the threshold, then the gain is progressively decreased. So it's squashed. Okay, and then the slope of that squash is what we call the ratio. And it describes the amount of squash. If it goes to infinity over 1, that's when you get a horizontal line that would become a limiter at that stage. Okay. Although with the time constants, there's a few more details here. So you probably know this already, but a compressor with many parameters typically has these two, threshold and ratio, but it also has parameters like attack and release time, which specify the time related behavior of this process. We'll talk about that in a bit. So let's look at the types of dynamics processors that we might encounter. Very often these are not spelled out, so typically you will have a compressor or an expander or a gate. But technically we actually make a distinction between downward compression and upward compression, and the same holds for expansion. So in the table you can read what happens to this signal. And two things happen. Something happens below the threshold, which is the left column, so what happens to the soft bit, and something happens above the threshold, namely something happens to the loud bit. So typically each of these will have one of these regions intact, a linear transfer. So what you've just seen labeled compressor and what you typically see labeled compressor is actually a downward compressor. So the soft dynamics are unaltered and the loud bits are becoming softer. But actually we also have upward compression, whereby we have the loud bits intact. So we have a linear transfer above the threshold and we have the soft dynamics becoming louder. So it's a slightly different thing from having a downward compressor with makeup gain, right? Because you could say, well, actually, if I do a makeup gain, so dial up the gain after the compressor, then the loud bits are back to loud. So they were softened by the compressor and then back again using the makeup gain. And then the soft bits, which were intact, are actually ending up being louder. So you can kind of compare it to the upward compression. But if you think it through, and that's what I'm inviting you to do here, you will see that there is a difference if you plot these transfer functions. Okay, so as you've seen the one before, I suggest you take some time, pause the video, take a piece of paper, and see if you can get these 5 transfer functions, little threshold line halfway on the input axis, and some kind of breakpoint around that. This will show you how well you understand the matter at hand. Typically, it's easy to understand and observe, but to rethink it, think it through, synthesize something based on that understanding is your true test. So please take some time to do this. Okay, now let's look at the solutions if you have tried and done it. So here they are. So what you see in each case is that halfway the input axis there is a break in the line. Evidently, it's a nonlinearity. And then you see what's going on. So with the downward compression, the left bit is linear and the right bit is squashed down. With the upward expansion, again, the soft dynamics are linear and the loud are this time made even louder. Now with downward expansion, this is where we get into having the loud bits intact and the soft bits change. And in this case, the soft bits are made softer. So an extreme case of downward expansion is gate, when the soft bits are not just made softer, they're muted altogether. And then finally below we have the upward compression, having it so that the soft bits are made louder and the loud bits are intact. So in this case you could actually see that if you push the downward compressor with the makeup gain that would shift the whole graph up, it is still not the same as the upward compression graph that you see right there. Okay, so let's look at some more detail about this, and we're almost done. So here's the transfer function of the gate. Typically many uses for it. You can attenuate background noise, but not independent of the incoming signal. So what you can do is when the signal is very soft, you mute the whole signal altogether. Typically these days, with much more advanced noise reduction techniques, we can identify this as an ancient and potentially useless technique in this context. However, in the creative context, in the creative realm, you can do quite a lot of things with gates. The interesting thing is that here we start to understand why the time constants, the slowing down of the control signal essentially is really crucial, because you can imagine that if you have a gate which is being triggered on and off very rapidly, then what you might get is a lot of clicking, and if there's quite a lot of clicking, the whole sound gets very distorted. So it is crucial to have the gate kick in slowly and release slowly as well. So typically we have parameters that describe this time dependent behavior here. One is the hold duration, right? So the gate will hold for a certain duration before it can be triggered back. And we also have the decay time, which essentially once the gate is triggered back, it will actually slowly release rather than making an abrupt jump in loudness. So this is fairly straightforward. And then a creative use of this, probably the most famous example of gated reverb, is when you use a reverb to get a very lush sound, and then once the tail is releasing, what you do is you cut it off, making it slightly unnatural but slightly more forceful, and kind of an interesting creative thing. There you go. Hello, Phil. Hope you're listening. Here is a sketch of what actually happens to the signal. Okay, so what we have here is a signal mixed with noise. That's the top signal. And then what you see below is the averaged envelope of that signal together with the threshold. So you see when only noise is present, then the amplitude is below the threshold, and when the signal enters, then it's above. And then what you get thus is the removal, total removal of these silent bits, which for this type of signal seems to work quite well. Now, if you look at the more natural acoustic signal, which has decay, then what you see is that with the gate, at some point, the signal will be cut off, and you see it, and you probably would hear it as well as slightly unnatural, abrupt ending of the signal. So this sketch relates to a gate without a decay time embedded. And you can imagine that if there was a decay time, that this would look slightly better. Okay, so let's look at the general structure here. So how does the process that does this look like? Okay, so we have the audio in, and again, only thing we do to the audio signal itself is change the gain of that signal. How do we change that gain? Well, we've been through a dial, we've been through a modulation source, and this time we have a signal, a control signal that is derived from the audio signal. And this is done using the envelope follower. There are many different ones. Typically RMS following is used for compressors, peak followers used for limiters. There's different designs, different things you can do, quite a lot of experimental stuff. In fact, if anyone's interested, on my YouTube channel, I have a good 2-hour lecture on just experimental compression using analog modules, which is something that you can code digitally as well, if anyone's into experimental stuff. So that's the basic sketch there. This is what we call a feed-forward processing of the dynamics. Kind of implies there is a feedback version as well. We won't go into all the details. I mean, studying the design and the analysis and the application of just compressors could take a whole master's degree, if not more. So evidently we just get to scratch the surface here. Nevertheless, very useful stuff that will allow you to play around with these tools with a more knowledge and understanding of what it actually is. Okay, briefly, just so you don't get confused, in this sketch what I have is a gain function, which is not the transfer function. So I'll just make a brief distinction here. The transfer function is what the system does if you look at it from outside. This was the input, this is the output. The gain function is the function that is inside the unit, and it actually takes the input envelope level and gives us the gain value from it. You see, so it's slightly different. And hopefully with this simple example you can understand that with the transfer function, if the input level is below the threshold, the output level is 0. But as far as the gain function is concerned, as soon as the threshold is crossed, the gain has to be 1. So the signal is fully intact. And if the threshold is not crossed, if this input signal is below the threshold, then the gain value has to be 0, so the signal is muted. Okay, so another exercise, if you're really digging this, you remember the one with sketching all the transfer functions? You can try to sketch all the gain functions for all the transfer functions. It does get complex, but maybe you find it fun, who knows. So last few bits about compressors. This time we won't go into expanders and the rest of it. So briefly, the ratio here, you see how it pans out. And my poor pen here, digital pen, is gone to sleep. It doesn't like it. I didn't use it at all. I'm sorry. It just stood there. Hello and welcome. Is it back? Almost goodbye. Make a little joke. Almost goodbye. It will be useful, I think. It's just that this set of slides has a lot of sketches. Once I run out of sketches, I'll probably need to draw more things. So finally, about compressor, we've said what it does. Typically, you can reduce the dynamic variation, can be really useful, reduce the attacks, get the sustains to be louder, depends what you're doing, can be very creative. One of the few interesting things is that it will change the timbre of the sound, especially if it is an analog or analog modeled compressor. It can be quite obvious. The other effect, which is not necessarily immediately apparent, is that it fuses sound sources. So if you have two different sound sources, you mix them and then you compress this mix, then they will start to interact with each other. Okay, that's one of the ways you can listen out for the amount of compression that is being done, is by just figuring out, okay, do these sound sources stay very stable and separate, or is there a dynamic interaction? When one goes louder, the other one goes slightly softer, or the other way around, or indeed, do they move together back and forth? What could be the case? And the other thing which you can hear also in relation, in listening to the relation between two mixed sound sources, you can also hear it with a single sound source. With the compressor, is that you can get a sense of it bouncing back and forth in space, with the attack going back or forth. So the thing is that if the sound source is becoming more distant from the listener, there are a few things that happen. Typically, the high frequencies roll off, and also the diffuseness of the sound increases. Okay, so if you just lower the amplitude, you will get a sense of changing distance as well, because with the distance the amplitude goes as well. So typically you get a kind of a set of conflicting cues if you just lower the amplitude, and that's what happens with the compressor. You typically just lower the amplitude. Okay, so what you will get typically is that the sound sources jump slightly back and forth. If you have a really good listening setup, you might be able to hear it in this fashion as well. Briefly, in comparison to the limiter, so what you see here is that the limiter, which is the third graph, is actually limiting the signal, whereas compressor typically allows it to come through a bit more. Okay, so that has to do with the ratio, meaning that above threshold some signal can come through as well. And then also, depending on attack and release parameters, what you might have is that the attacks come through a bit louder. So all these settings can make quite a difference. A few more bits about limiting. Okay, so as said, it will actually make sure that it never crosses the limit. Expansion, briefly, just for reference and completeness. I've probably run a bit out of time, I have no clue, but I hope you've enjoyed it. Any questions you might have, I will gladly respond to in person. Take good care and goodbye.